Binary trees are a data structure consisting of nodes with at most 2 child nodes. They provide a hierarchical structure to store and access data non-linearly. Binary trees are one of the foundational data structures and form the basis for many other data structures. Mastering the fundamentals of the binary trees is crucial in the field of computer science, as binary trees and their variants are encountered across many disciplines and utilized in countless applications. In this video, we aim to explore the fundamentals of the binary tree. We will first start with the structure and properties of a binary tree, as well as how to create a binary tree from an array. Following that, we will discuss the basic operations performed on binary trees with specific focus on the 4 types of traversals. To close, we will enumerate the various applications for binary trees in different computer science disciplines. Overall, this video will be a high-level overview of the basics of the binary trees, which will give you the knowledge to be able to implement them in your own code. Binary trees consist of individual nodes that have 3 attributes: their data, the pointer to the left node, and the pointer to the right node. At the top of the binary tree is the root node. The root node serves as the beginning of the binary tree, where the user can begin to access the rest of the tree. The pointer towards the left and right node are called branches. All the way at the bottom of the tree, the final node lacks a left or right node. These nodes indicate the end of the tree. In keeping with the tree theme, they are typically called leaves. Leaves pointers points to null. Finally, similar to family hierarchies, nodes are named based on their relative position in the tree. Parent nodes have a left and right node, which are called children. For example, C is a parent node with children nodes F and G. Ancestor nodes are parent nodes or parent nodes of other ancestor nodes further up in the tree. Here, the ancestor nodes of F are C and A. And finally, subtrees are subsets of a larger tree. In this case, B, D, and E are a subtree of the larger complete tree. One important property of binary trees is their height. The height, as defined as the longest path from the root to any leaf, illuminates various properties about the tree. For example, the maximum amount of nodes in a binary tree in total, with a height of h, is 2 to the power of h minus 1. For this tree of 3 levels, the maximum number of nodes maintained is 7, or 2 to the power of 3 minus 1. The height of a binary tree is important in determining the time complexity of various binary tree algorithms which traverse from root to leaf. These complex algorithms will be discussed in a follow-up video. Binary trees can be further classified depending on certain structural properties. Perfect binary trees consist of nodes with exactly 2 children, and where the leaf nodes are all at the same level. Next, degenerate binary trees consist of nodes with only 1 child. Skewed binary trees are a subset of degenerate binary trees with only left or only right children for the entire tree. Degenerate and skewed binary trees have the same structure as a linked list and are the most inefficient tree structure to perform operations on. Finally, balanced binary trees are trees with the height of O log of n. Balanced binary trees are the most efficient when performing operations on them, since traversing from the root to any leaf node occurs in O log of n time. In practice, the classification of binary trees is not a necessary knowledge in order to code them. However, this demonstrates that the binary tree has structural variability, allowing for flexible implementation and leading to variable performance metrics. There are 2 ways to represent a binary tree. The first is with just the pointer to the root node. The second way is by constructing it from a given array. The translation between array and tree follows a simple formula. To generalize this process, for a given node constructed from an index p, its left node will be constructed from an index 2p plus 1 and its right node from 2p plus 2. Given that the root node comes from index 0, the rest of the tree can be filled out following that constraint. If an array is null at a given index, the no node is added to the tree, and that slot is skipped over. Array representation of a binary tree is useful for informal shorthand, especially in writing, when enumerating the entire tree structure would be inefficient. Overall, the structure of a binary tree is simple yet elegant, which leads to creative applications and intriguing problems. Now that we are familiar with its tree structure, let's see what we can achieve with it. As with all data structures, binary trees have 3 fundamental operations: traversal, insertion, and deletion. In this video, we will first be focusing on the 4 most common traversal techniques: in order, pre-order, post-order, and breadth first. Once we solve these, we can utilize these techniques in insertion and deletion. For each of the 4 traversal methods, we are looking to populate an array from a given binary tree. The resulting arrays will differ based on the utilized traversal method. The first 3 traversals, in order, pre-order, and post-order, are depth-first searches, while the last is a breadth-first search. Depth first searches iterate completely in one direction before backtracking to cover every other possible direction. Breadth first searches completely explore one level before continuing on to the next level. Depth first uses a stack, while breadth first uses a queue. These distinctions will become more apparent as we cover traversals. First, in-order traversal. The order of this traversal goes left to middle to right. Starting at the root, we traverse down left as far as possible, adding to the stack as we go. Reaching the leftmost leaf D, we append D to the resulting array. Since we are at the bottom of the tree, we will pop D and start backtracking to explore the other right-hand branches that we already passed by. Return to the next node of the stack, which should be the parent node B. Add this parent node to the array and verify the existence of its right node. In this case, there is a right node, E. Add E to the array, pop it from the stack, and backtrack again to the parent B. Since the left and right nodes of B have been exhausted, pop B from the stack. The next node in the stack is A. Since A's left subtree has been fully explored, we now add A to the array and continue this process with the right subtree. Going down to the left, add C, then F to the stack. Add F to the array and pop it from the stack. Backtrack to C and add C. Traverse right to G, add G. Backtrack to C again and pop it since we were done. Backtrack to A again and also pop it. With an empty stack, in-order traversal is complete. The general process for in-order traversal is as follows. For every node we encounter, explore its left subtree as far as possible. Once we exhaust the left subtree, add the parent node. Then, explore the right subtree as far as possible. Next, pre-order traversal. This traversal process is similar to in-order, but instead, the order of nodes goes from middle to left to right. Starting at the root, we traverse down left as far as possible, adding to the stack. This time, we also add these nodes to the array without waiting. So we add A, then B, then D. Once we reach the end of the leftmost leaf D, we pop D and start backtracking, taking the right subtree where possible. We backtrack to B and turn right to E. Adding E, we pop it. We then backtrack to B and pop it as well, since we are finished with both its subtrees. Then we backtrack to A to explore the right subtree. Traverse down to C and add C. Traverse down to F and add F. Then backtrack back up to C and turn right to G. Finally, add G. We are done here, but officially we backtrack all the way back up to A. In other words, starting at the root node, for every node we encounter, append the node to the array. Then, explore the left subtree as far as possible, followed by the right subtree. For the final depth-first traversal, we have post-order traversal. This is similar again to the previous two traversals, with an order of this traversal that goes left, right, middle. Starting at the root, traverse down left as far as possible. Once we reach D, add D to the array. Since we're at the bottom, backtrack to B and turn right to E. Add E to the array. Backtrack to B again and add B to the array. Backtrack to A and start exploring the right subtree. Add F, then G, then C. Finally, since both the left and right subtrees are exhausted, add the root node A. In other words, starting at the root node, for every node we encounter, explore the left subtree first, followed by the right subtree, and finally add the parent node to the array. Finally, breadth first search. Breadth first search is an algorithm where every level or iteration is explored exhaustively first before moving on to the next. For binary trees, it is essentially the reverse of creation from an array where we process nodes level by level. We will be using a queue to perform breadth first search. First, initialize the queue to just the root node. Push the root node's left and right nodes to the queue. Now, pop the root node and add it to the array. Continue popping the nodes from the queue and pushing their children nodes to the queue until all nodes in the tree are exhausted. To generalize this process, we start with just the root node in the queue. Every iteration, we pop all the nodes from the queue and append it to the array. Every node we append, push its children nodes to the queue. Repeat until the queue is empty. All these traversal algorithms have a time complexity of O of n, since we are iterating through every node in the binary tree. All three depth-first search traversals have a space complexity of O of n, as in the worst case, every node in the tree is stored in the stack at the same time, as in the case of a skewed binary tree. For breadth-first search, the maximum number of nodes that will be stored in the queue at a given time is the width of the binary tree, since we process the tree level by level. Overall, the traversal complexities, even in the worst case, are above average for data structures and will outcompete or at minimum be equivalent to a linked lists. For this insertion example, we are trying to add a new node in the first available level order position. This means, while iterating down a binary tree, level by level, we want to add this new node as either the left or right child of a node, whichever we find empty first. In this case, we can use breadth first search to traverse down to node C and discern that its left node is empty. We can insert the new node as node C's left node. Insertion has a time complexity of O of n, as in the worst case, we have to traverse through every node in the binary tree before finding a suitable insertion point. The space complexity is also O of n, since in the worst case, we have to store every node in the binary tree before reaching the insertion point. There are other cases of insertion in binary trees, such as inserting where a node already exists, requiring restructuring of the entire tree, but I will save those for a future video. Finally, deletion of a node in a binary tree. Let's delete node G here. Again, we have to iterate through the binary tree until we find node G is either the left or right child of a node. Once we reach node C, we can determine that its right node is the node that we are looking for. Simply remove the reference to the node by reassigning the right node pointer to null. Now, node G is deleted. Deletion has a time complexity of O of n and a space complexity of O of n for the same reasons as insertion. There are other cases of deletion, such as deleting a parent node, which requires careful handling of its children and subtrees. But again, I will save those for a follow-up video. The binary tree data structure is the prototypical form of various specialized data structures and algorithms. Its basic composition can be easily exploited and molded into particular structures that serve the problem at hand. First, binary trees are used in sorting algorithms, such as heap sort. A given array is to be sorted by converting it into a binary tree and manipulating its structure by swapping nodes around in a process called heapifying. At the end of the algorithm, the array will be sorted in ascending order. This video will not go into the specifics of heap sort. I will leave that for its own video. Next, the binary search tree is a special form of a binary tree where every node's value in the left subtree is less than the parents, and every node's value in the right subtree is greater than the parents. This holds true throughout the entire tree and all its subtrees as well. This constraint makes performing operations on the binary search tree more efficient when compared to a regular binary tree. Branches in a regular binary tree lead to random values, requiring an exhaustive exploration of all possible combinations. Binary search tree branches are clearly defined as greater or less than the current node. Therefore, the user can systematically make an informed decision at every branching path. With a binary search tree, we can perform another type of sorting algorithm, the tree sort. We can perform a depth-first search on the tree and retrieve all its values. These values should already be in sorted order due to the structural constraint of the binary search tree. Red-black trees are another variant that marks its nodes as either red or black and maintains a balanced structure through special restructuring algorithms. As we discussed before, the performance of operations on a binary tree is dependent on their structure. In the worst case, a degenerate or skewed binary tree results in an abnormally high time complexity of O of n. Red-black trees are a solution to this problem by ensuring that the tree is always balanced regardless of insertions and deletions, leading to a consistent time complexity of O of log of n. Another type of binary tree is the decision tree in the context of machine learning. Similar to a flowchart, a decision tree is a series of sequential decisions performed on a set of quantifiable or Boolean parameters that result in the classification of that set. Here at the root, we started out with a set of 12 worlds, each with their own set of values for the variables x, y, and z. As we traverse down the list, the set of worlds is split up into two subsets. One subset contains the worlds that satisfy the x node constraint, and the other subset contains the worlds that did not satisfy it. This is analogous to making a decision about x. This process continues for every node in the tree, and at the bottom, each world has been classified. Binary trees have many more applications, a lot more than I've been able to fit into this video, all across a variety of fields such as data management and machine learning. While following the same general fundamentals, each variant tackles a different problem with their own set of constraints and operations. Red-black trees and binary search trees definitely deserve their own videos, as they're pretty common and pretty complex, so I'll be coming out with a follow-up 201 and 202 videos covering these variants in more detail. Binary trees are a nonlinear data structure capable of storing data and performing rudimentary operations very efficiently. Its succinct, hierarchical structure permits for a wide range of applications and is the cornerstone for many challenging algorithmic applications in the field of computer science. Hey everyone, if you enjoyed this video or learned something, definitely check out the previous 101 video on linked lists, and be sure to be on the lookout for the follow-up video on binary search trees. Thanks for watching.